Record. Okay. So we're going to talk about our 2017 season. We definitely had an interesting season in that we changed our robot probably more than any robot we've ever had. Discounting 15's entire transformation. 17 is probably a close second to that, and we just did it pretty consistently through every event. We added new things or changed up things as we were going. Whole subsystems either moved or got changed or added, to where the robot was pretty unrecognizable from event to event. We'll start by looking at the game animation for 2017.
Welcome to the first robotics competition and the
2017 game, First Steamworks! 2 adventurer clubs, alliances of 3 teams each, prepare for a long-distance airship race by collecting fuel to build steam pressure, installing gears to engage rotors, and climbing aboard for liftoff. The airship best prepared for flight when the launch timer reaches 0 wins. Matches begin with robots touching their Alliance station wall. Teams may preload up to 10 fuel elements and 1 gear on each robot. Fuel is available in hoppers placed around the perimeter of the field. Additional fuel and gears are available at the Alliance loading station. During the first 15 seconds of the match, the robots are autonomous. They work to reach their baseline, score fuel in the boiler, or deliver gears to the airship. During the following 2-minute and 15-second teleoperated period, human drivers remotely control their robots. They continue to gather fuel from the field and the hoppers to score in the boilers. They also collect and deliver more gears. Human players located behind the Alliance station wall deliver gears and recycled fuel to robots through the loading stations. Steam pressure builds as fuel is added to the boilers. The high boiler produces more steam per unit of fuel than the low boiler. The more fuel scored in the boiler, the higher the steam pressure climbs. Alliances earn points for the amount of steam pressure built, and pressure over a certain level earns an additional bonus. Each airship has 4 rotors with some gears missing. Oh dear. Gears delivered to the airship lifts are retrieved by the airship pilots, who then place them in the gear train to engage and spin up the rotors. Each rotor requires an increasing number of gears to become engaged. Points are awarded for each airship rotor turning by the end of the match. Airships spinning all 4 rotors also earn an additional bonus. Towards the end of each match, pilots deploy ropes for their robots to climb aboard. Alliances earn points for each robot secured aboard the airship by the end of the match. Be prepared. It takes time for the boilers to process fuel for the airships. Fuel put in the boiler near the very end of the match may not get processed before the airship takes off. The alliance with the highest score at the end of the match earns the win. Ready your robot, fly your banner, and prepare to take flight with this year's first robotics competition, First Steamworks! Ha ha!
Okay. Yeah.
He was excited.
What?
He was excited.
Yeah, he's some sort of. Does anyone remember who this guy is? They brought in someone to do the voiceover, and he added. I'm assuming he added that stuff. I can't imagine the weird laughs were in the script.
Yeah.
But this animation drives me crazy. I've never been a proponent of the heavily themed games as far as they are now. I think there's some line, and I think they cross the line sometimes. And this is definitely some version of it, right, where everything's in costume and
yeah, the costumes.
They went so far. They just dove down this we're just gonna really be into this steampunk thing, but only sort of, and it's just gonna be weird, and I don't know. It's fine to a point, and then it starts just getting almost alienating to some people, and yeah, just being too much. This game in general had lots of interesting things. They definitely pushed the boundaries of what had been done in FRC before, right? We've looked at basically every game from 2012 to here, and you can tell there's a lot of different things, right? big key things are like there's people in the middle of the field, right? That's never been a thing before. So like that was cool. That was a interesting concept that they did. These like side hoppers were interesting because the way like field reset exists, right? You have to put them all in here, and then your robots can go and push these hoppers and get balls directly loaded into them, separate from like a human doing it. We hadn't seen any like automated ball dumps since, if you go back to like the 2004 game, there's an automated ball dump at some point. Not necessarily automated, but like a mechanical ball dump. And you had the boilers. Is there a better field image somewhere? So yeah, you have the boilers on each end, and if you notice, the field isn't symmetrical for the red and blue side, right? The blue side has the boiler on their left, the red side has their boiler on the right. This was a big deal because this meant some teams' autos worked better if they were on red or if they were on blue. Right, because you have this right auto and you have this left auto. So that was a huge deal. And that's actually, we'll get to in a second, one of the ways our robot is built to account for that a little bit. And you also have this game where like there's two very distinct game objects for the first time in a long time, right? You have the fuel and the gears. So you have to figure out how much of your robot is going to do one or the other. And you also have this really weird point weighting scheme for the entire thing. Can I find that exact spot? Maybe. I don't know where that is. Oh, there it is. So yeah, so during teleop, you need 3 balls in the top to score 1 point, and you need 9 balls in the bottom to score 1 point.
Oh, geez.
Yeah, they completely like priced themselves out of the bottom goal being usable at all. Like it just makes no sense especially with the weight of the gears and like just making sure you got all of your gear stages.
I think it would make sense if it was like 5 or 6 balls, but 9 is too much for the bottom.
No, it didn't even make sense.
No,
There's enough arguments. Like if you watch you can go find back from that time, like arguments for what the correct point scoring weighting thing would have been, and it's just really hard to get right because of the amount of like the skill level gap in like the best shooters to like everybody else. Basically, like I mean that gap was the top very few robots who were really shooting well. And then just everyone, and it doesn't really make. If you don't do something like where it is, those top few scorers can just like outpace everybody and run away with the game. But because they didn't do it that way and like kind of kept it down, it means that nobody else should even touch the fuel because it's just not worth it. In auto, it's a little bit better, right? A ball in the high goal, every ball in the high goal is worth 1 point, and every 3 balls in the bottom goal are worth 1 point. So your auto fuel makes a lot more sense. Teleop fuel for most teams was just not valuable. The few teams who could really, really score, it ended up basically being kind of that tiebreaker where you still had to play the gear game and had to play it well to be able to advance. But then if you could do that, you ran out of gear points because there was the step function on gears. Is that in here somewhere? I don't even know if it is. Right, you only get 4 rotors that you're able to score.
Wait, so were the points for the lights thing in the middle thing? Is that what the pressure was?
Are the points for the what?
Were the points or the 3? I'm not sure. What were those lights for? Were those the points that the pressure from the boiler builds up to? In the middle, under the spinning thing.
Oh yes, I think those are. I think these lights are your pressure, which was called KPA that year. So if you got like 40 KPA was what you were trying to get to your ranking point and bonus points in the playoffs. think it's 20. I'd have to look at the rules again.
Yeah, and you basically stop shooting after you get that if you can shoot.
Right. So like basically you were shooting to get to 40 in qual matches if you already basically knew you had won the match, right? You were trying to do whatever you could in auto to get there. And then you would go and run the gear game, basically try to get the match in hand where you knew you were going to win. And then you would try to shoot to 40 and then basically stop because that's all you needed was you got the ranking point if you could get it to 40 kPa. In the very high end, when you start looking at like champs playoffs and like Einstein, you had to keep shooting because largely the match was decided by fuel at the very high end because they were finishing the gear game, right? Because your gears were completely topped out and you only got points for gears if they turned a rotor, right? Each individual gear didn't get you points. So your first rotor was actually free because there's a gear that starts in the airship. So all you have to do is remember to pick it up and put it in this slot. That is not something that always happens. But ideally, if you remembered to pick it up off the floor and put it in this slot, you were given 40 points. From there, you had to get your next 3 gears all had to be done, which I do not remember how many gears that was required. It was 1, right, for your second rotor?
I thought it was 12 for 4.
12 for all 4 sounds right. So the third one is 6. So that means it's 2 and 4?
Yeah.
Is that right? Yeah. Oh, it's 2 and 4. That makes sense. Yeah, because you've got 2 gears.
Because you stopped after 3 a bunch of times.
Is it 2 and 4? Something like, yeah, that sounds about right. Because, yeah, the last one I think is 6. Because it's a lot more to get your last rotor going. We can look it all up in the rules. It doesn't matter. But all you need to know, it's like the stair-step function of points where if you got, let's say it's 6 to get the first 3 rotors. If you got 6, you got 120 points. If you got 9, you still only got 120 points. Right, so at some point you just stopped scoring gears if you knew you couldn't either score anymore or you'd already scored enough. You would just quit scoring gears and go play defense or do whatever you could to try to win the game because there wasn't a lot else you could do if you knew you weren't going to get to your next stair-step function or you already completely maxed out your gear score, which leads to kind of chaotic end of matches where you're trying to like push around other people and do things like that. What am I going back to? Okay. So our robot in 2017 was at the very beginning not very good. We had a weird problem that year in which we prototyped, but we didn't actually prototype well, right? So like we kind of went through the motions of prototyping, but then didn't actually use what we learned from testing the prototype to actually influence our design. So like we built out basically almost a full wooden version of the robot, which is very reasonable, except the wooden version of the robot basically didn't work and we didn't change anything really going to the metal version. And that's defeats the entire purpose of prototyping. So like we changed little things, like we tweaked things, but we definitely didn't get to the point of like, oh, we never got to the point where the prototype worked to allow us to build a metal version that also worked, right? We just like made slight improvements, but almost like a second version of the prototype as the competition robot, and that also didn't work. So I think part of that was just like we were pressed for time a little bit, so we were worried about that. But there was no reason for us to do that, right? We could have changed our scope a little bit, changed up how we wanted to do things, and allowed us to do something that worked better. All that being said, we were again still finalists at our first event. So
first 2.
What?
First 2.
Right, we were actually finalists at our first 2 events, right? There is a short video of the robot mostly working before we go into the CAD.
It's automatic. I got a way of making noise. The power to destroy no
This is the robot at Alamo.
victory is all you need. So cultivate and plant the seed. Hold your breath and count to 10. Just count to 10. I'm gonna make it rain, so ring the bell. I know it
I forgot that scene is in there. So the shooting scene is hilarious, where it shoots the balls, because it very much, you do not see where the balls go.
so ring the bell.
It shoots them and then it cuts, because those balls definitely don't go in the boiler. So that's fun, because Alamo, our shooter, was not running well. So we can go through kind of looking at some of the prototype stuff. I don't even know what. Oh, that's like the winch climber, just making sure we had some sort of climber that's mounted on the football shooting robot that we had that existed at some point. We will go through and look at some of the CAD of some of these mechanisms here in a second. Is there any parts of this? Yeah, and then there's a lot of design revisions where we made pretty huge improvements to things as the year went on that made a lot of things a lot better. One of the biggest things was the shooter change we can talk about here, because I don't have the CAD of the original pulled up. The original shooter was basically completely non-functional. Like, balls would kind of go through it, but it would jam very often, and there was no sense of any kind of accuracy with how this was supposed to work. It was supposed to be like these multiple belt things, which were all what am I thinking? They were all shoulder bolted hex shafts, but you still like kind of build up the whole hex shaft with like all these belts, which was really, really hard to do. The assembly process was a pain. There were 2 rollers at the top that would kind of pop the balls out, because kind of our goal was largely just to like throw balls in the air and hope some of them went in. It's not a great plan. There was also this weird problem where we were trying to like block off some part of the path. We would have like servos that would move up and down or something to only allow 2 of the 3 columns to be able to be firing. So the idea was like, even if we couldn't line up exactly right, we would figure out which 2 paths were like closer to the goal, and we would like block off the other one. That never existed and never worked right. There was just a lot of, because there were so many belts and things, it never could move fast enough. There's like a lot of binding. The shafts were too long, so like the belts weren't quite tensioned perfectly to where you'd get like the shaft was like bowing towards some parts of the belt and things. It was just a lot of not greatly engineered concepts for what we wanted it to do. Yeah, so then what we ended up doing was, after our first event, when we knew that shooter was not going to work at all, we looked around a little bit and saw who else had designs that we thought we could use and integrate into our robot. One of those teams was the Killer Bees 33. So I emailed Jim Zondag, who's their head coach, and I was asking him questions about it, and he actually was nice enough to just send us part of their CAD for it, just their shooter assembly. And one of the things they did that was really interesting to us, that allowed for us to be able to do some things, was that their shooter basically was modular, so they could pick the whole thing up, turn it around, and have it fire the other direction. So when we look at it in the CAD, we'll see it. But basically, it shoots out the side of our robot, because we really just wanted it to be able to do auto well. So you could flip it up, you could flip it around, so that whether you were red or blue, you could shoot from either side. So the way this kind of process worked was, we got the CAD from them, and then Will Smith at the time took it and made it into a sheet metal design that we could have Solarcraft make most of the parts for us relatively quickly. And we actually had it mounted on our robot for our second event. It was not working well, and basically never really worked well until IRI was when we could actually run the auto and shoot well. Okay, I'm gonna flip to the CAD of this robot now. So this is definitely by the end, one of the most complicated robots we probably built. There was a lot going on. So the drivetrain, let me see if I can stop just like flailing around a little bit. All right, there we go. Okay, so the drivetrain was a 6-motor drive. It was just 4 wheels, so it was 2 traction and 2 omni, and at some point it was all omni for a little while. We wanted to build in, because of like how much space we knew like the ball storage and everything was going to take, we wanted our wheel wells to be pretty tiny. So we built the gearboxes into the wheel wells. So it was a single gear reduction from the motors. Then the sprockets would drive to each of the outside wheels. And that part worked fine. You can see there's a sprocket mounted here that doesn't go anywhere. The plan was for that to be the climber. So the original plan was for a chain to come up and like spin the climber, because we knew we'd only had to spin up this like tube at the end of the match. We were like, oh, we'll just drive into the rope and we'll just drive and it'll be fine. And the concept kind of worked, but it just wasn't necessary. Like we had so many motors in reality, we didn't need to do that. So we eventually pulled that off, and you'll see that this sprocket ends up doing nothing in the final version. Trying to think, we did have integrated handles, so we had sheet metal handles that were integrated that had the power switch mounted to it, so it was easy accessible. This side had our pneumatic gauges mounted into it, and some things like that. This is largely a very simple drivetrain. There's not much to it. It's just the parallel plates that are sheet metal C's again, with just a normal C kind of crossing the back. All of this was largely very not a lot of complexity in this drivetrain at all. The front had to have a cutout for our fuel intake and gear intake. The gear intake came down kind of inside of this frame as well. There were some really weird problems in that there's another, when you see the intake mounted, it gets mounted in here. So that means there's like this weird tiny gap right here. So if you needed to like get to this nut, it was painful. And if anything else that would fall in here, just was not good. There's nothing there. There was no way to like get things out of here. We should have probably put some holes in this or something to be able to access more. And we just didn't. This brace that crossed here sat on top of the belly pan. So the belly pan was plywood again, like normal, and it would be mounted on top of this plate, on top of this plate, and under this plate. And that led to some weirdness in that all of the wiring had to go through this bar. So like the PDP is basically mounted right here. And most of the talons and all the speed controllers are mounted along like this line, basically, of the belly pan. So all of the wiring had to come around and kind of get mounted in through here, through this gap, and just led to a lot of complexity in the wiring path, because everything had to go through these channels or these cutouts in this C channel. What else? There's some nice little unique features. So this was a before we had, we weren't doing continuous chain at this point, we were doing master link. So this little rectangle cutout is built in so that you could get to the master link and put it in or take it out. Because we had these like braces going between the chain runs. So because of that, you couldn't, doing continuous chain would get really awkward, as you would have to take the braces out every time if you had a normal continuous chain, or try to like somehow push the pin in and out while it was all mounted. So because we couldn't really do that easily, we did think enough about maintenance and things to be able to do the master link there. These holes here to be able to tighten the bolts going into the sprocket without having to take anything off or anything. So if you rotate them, you can get to a point where all 6 of these are showing, and you can tighten all 6 bolts. In reality, you could do it with just one, right? And then just rotate the wheel and get all 6, as long as you have one of those holes properly. If we have bigger cutouts, it also works. I'm not sure why we thought it was necessary to have singular hole cutouts instead of just larger it'd been perfectly fine to have larger cutouts for that. Let's see. So yeah, so we did have to have this shaft is a live hex shaft to be able to transfer torque easily to everything, but in reality, it didn't have to be. Everything's bolted through here, so this could have been not a hex shaft. I think it was a live hex shaft, partially because we were going to do a there's an encoder mounted on here, which did exist in the final robot. So this shaft had an encoder pressed into it and then clamped onto it, so we could have so we could figure out, we would know where our drivetrain was going. Because if everything is dead axle, it gets a lot harder to have an encoder anywhere. Okay. Coming back to the rest of the robot. So the original version had different ball intake plates that the gear intake was mounted on. But we'll look at this version because this is one we have in CAD. It looks like you have these two motors that are in the same spot roughly. And there's actually, I remember this being very problematic because this is basically the frame perimeter. This might be almost over frame actually. It's real close. I think in the final version, it's like, yeah, like that shaft is probably actually past there. I don't know if it is in the actual thing. I think it's a little bit inside, but I remember the wiring having to be incredibly close. So it wanted to stick out of frame, and that'd be illegal. We would fail inspection if we did that. So ideally, we never design anything to get that close anymore. We also wouldn't, because now this is a Neo 550 or something, and it's super tiny, which is nice. But back then, motors were, we say large, but really a 775 Pro isn't that large compared to other things it could be. But with how tiny the Neo 550 is, we can package it anywhere now. But yeah, so we had the same kind of issue on, I don't think this one actually ended up having an encoder or anything. So this side was probably fine. This side was double reduction with encoder. So this side was really close to the edge. So this one is what moves the gear intake in and out, right? So you have this versus planetarian motor driving this gear, and this gear has a hub spacer and is bolted to this entire, this arm assembly, right? And it's mounted on a bearing. So this can move up and down, and it doesn't affect the rotation of the shaft at all. Does that make sense?
That
Right.
makes sense.
Yeah, so it's on a bearing. So it's basically, it's using that shaft as a pivot, but it doesn't actually care what this shaft is doing at all since that bearing is there.
Okay.
So this side is a gear reduction that's basically the same gear spacing as that other side, except it has, this gear is actually a hex gear, and it's mounted on here.
Oh, okay.
So these shafts are all hex shafts that are bored and tapped for a shoulder bolt to come in from the outside. So this was actually one of those spots that was incredibly difficult to do anything with. So you had this like shoulder bolt here, but like ran into this plate. So I think at some point we cut part of this plate back to make it easier to install a shoulder bolt here. But so that shaft, so this motor would actually spin this shaft. So this was basically the fuel intake that only sort of worked. And largely its main purpose was to get balls out of the way of when the gear intake needed to come down. Because if balls got like trapped in here, then the gear intake couldn't come down on top of them. So it never really intaked balls well. It would jam pretty constantly because we squeeze them through such a small gap. So like if you look at how big the ball is, this gap is way smaller than the ball. It did not ever really do what we wanted it to. It kind of worked on occasion, but it was not good. Yeah, so this motor would drive the gear intake down. We had some hard stops that were like catted into it, so this would hit the hard stop. The gear intake itself went through a lot of iterations because basically one of the things we learned to never do again. This is rotate. Oh, it does rotate. Cool. So when this is down, and this is actually in the upgraded version of this gets flatter. So we were able to lower this pivot. In the original version, this pivot was higher. So when we actually were to intake a gear, this was like almost down to there. So the gear would have to
wow.
go up this kind of steep angle. Let me get flat so you can see for sure what I'm looking at. Yeah, so this was higher. So the gear would have to come in and like kind of angle up. And because of that, this edge here had to be really, really thin. And the only way we could do it was we ended up having, this is like 30-second carbon fiber that would just be like sitting there, and it would like flex and then allow the gear to come up. The final version got a little bit better when this got flatter. It still wasn't perfect, but it was definitely better than our original version. And one of the biggest problems is just this span down here, because it was partly sheet metal, to be able to get thin enough, it would this would bend, or like the carbon fiber would crack. So we would be doing basically like as bad as our drivetrain triage was at Dripping Springs, where like every match we were just like trying to we were fixing weird things on drivetrain. For Hub City, especially our first event where we were super reliant on this, and it was the first time running it, we were just that was mostly Witchery or Jacob and Sarah would just be like would be just constantly taping and like redoing parts of it, and like trying to figure out how many matches we could like keep like parts of it through before having to replace it if it was broken enough, just to make sure we had enough to be able to like run through playoffs. It was not great. The original version of this had like this top panel come all the way over. But yeah, it was basically, there was compliant wheels here and a little bit of a belt to spin the back shaft, and it would just kind of store the gear inside and then run it along these ramps on the outside. And it mostly did its job. Like, we had a pretty good gear intake for the first event. It worked. We were able to hang a reasonable number of gears for our first event, where not everybody could put up any gears. And that did allow us to get to the finals. Yeah, so like that coaxial thing was part of the design from the very beginning, and it mostly worked. Where this was always the ball. This was kind of always the ball intake shaft was always going to be spinning at a different rate than the pivot that was being used for the gear intake. Ideally, if we ever do this again, we know to get it completely flat, and it makes everything so much easier if you can just put a flat thing on the ground to pick up the gear. And like just a small piece of Lexan or something that's easy to replace, that you can like sand down and get a thin edge on just that front edge instead of trying to do the whole thing as thin. Because the carbon fiber was not worth it. Trying to like machine carbon fiber, left with like carbon fiber fibers everywhere. It was not fun, like itching arms and stuff. Just overall not good. Okay. The other part of the robot from that mostly existed from part of the beginning was the climber. So after the going into Lone Star, we realized we were gonna have to move a lot of stuff. Lone Star was our second event, so we knew we'd have to get rid of the weird giant shooter would leave, but that was also where our climber was mounted. So we moved the plates from there, and we moved them forward, or they were kind of like mounted to it, kind of off to the back. They weren't exactly on the shooter, but they were their own separate plates. So we moved them forward. So the climber was on the very front of our robot, and these like wedge things were there to kind of like help guide the rope in. So you could make rope in 2017 was a whole complicated thing of like what was a rope, what was allowed on a rope. It took a couple days for them to eventually say that like Velcro was a legal part of a rope. And so we were able to sew Velcro onto the rope. So then you just had to have the hook part of the Velcro wrapped around your drum here. It would drive in, it would grab on, and then you would be able to like spin up and just lift your whole robot up that way. One of the things we tried to do was make sure we could climb very, very fast, because the fastest you could climb meant you could often get like a last second gear in or something. So we ended up putting 4 775 Pros on our climber to drive it as fast as we could. It was somewhere sub 2 second. I don't know what our actual hand clocked. Like the math said it was sub 1 second. I don't think it ever actually was. But it was very, very fast at the end. Once we were really running everything full out. This was also not designed awesomely. This hub was just pressed into the tube spinning in bushings, and he had to like bolt this in, so it became really hard to take any of this out because to like get the hub out was not easy at all. Because we had it on both sides too. I think the original plan was only have it on one side, so you could kind of pull it all the way out. But once you do it on the second side, it makes it very hard to get out. So I don't remember if it was pinned or bolted. It might have been pinned, to where you'd have to like press a pin out somehow to take it apart. Yeah, we were overly reliant on versaplanetaries for a long time, where now there's very few on our robots. Almost every motor ran through versaplanetaries back then. Okay, before we get to the shooter, we can do the other gear thing. So this was the last major addition to the robot, which was the gear backpack, is what we called it. We basically knew, so at Lone Star, we had basically done this front climber assembly. We had some part of the intake exist. I don't remember if we had changed these plates or not going into Lone Star, but we at least had the gear intake. The gear intake was still up here on some version of it. But we knew that wasn't quite enough because because of all the problems we knew we would have with the gear intake, if we were constantly relying on it to be our only gear mechanism. It was relatively fast, it worked, but only if it didn't like ever get like run into, basically, or if we didn't run into anything with it. So that was actually probably the biggest problem, was if we ran into a wall or anything with it down, it just was not designed to take that hit. So we knew it would cause problems. There were matches where we couldn't score gears anymore at some point because we would do something to it. And we knew we could be faster if we could human load gears in some way and be able to score them with a human powered system. We had looked into figuring out how to like human load the gear intake, which some teams were able to do relatively well, to where like when this is up, they would build a ramp that would allow the gear to kind of fall into it when it was up. And we had tested some things and we had designed some things, and we never really liked any of it. Just kind of the way this was stored and the way we wanted to do things, it never really worked. So we're like, okay, we'll just figure out how to do it light enough and with the space we have in the back, because we also knew we needed something to fold out over the bumper to let balls fall into the shooter too if we wanted to get the Auton shot. So we already knew we were having to put like basically some ramp panel down to pull balls into this area. So like, okay, so with that, we have 4 inches largely from the back of the robot to where the shooter's gonna sit. Can we put a whole gear thing in there? So we figured out we could, and this is actually probably one of my favorite mechanisms we built, because this thing actually worked largely pretty well, and it was pretty, not necessarily simple, but did its job in a relatively small space. It's 3 pneumatic actuations, so there's 3 cylinders on each side, each set controlled by their own solenoid. So you have the, let's see, where do we want to start? I guess we'll start from the back ramp. So this back ramp here, the one that has these side wings on it, let me see if I can change some colors, because this is going to get confusing if not. Maybe SolidWorks.
It's slow.
There we go. Okay, because these are like on top of each other, so if you don't change the colors, they look the same. Okay. Okay, so now we have a purple and a green one. All right, so this purple one is the first ramp. So this is the one that extends the furthest. It extends with the cylinders up at the top here. I think, is that true? Yes, that is true. Okay, so these extend there. There's actually this like gap. There's this cutout right here in this inner panel because most of the time this green panel is folded up completely flat to this bar. So like it sits pretty much entirely flat up against this piece of extrusion. So when we go to get a gear, the green panel is folded up vertically and we push out the purple panel so that the gear slides in, it hits the green panel, and it slides down into this little holder for the gear. There are this thing, which I don't know if I can actually get to select. It's going to be like impossible, isn't it? Oh no, there it goes. Okay, so these things are bent. They're not bent right now, but they're bent in real life. They're bent down and they help guide the gear into its little spot. Excuse me. Let's see if I can I unflatten that? Oh, maybe not. Oh, there it goes. Okay. Okay, so yeah, so that is, so those are bent down.
Oh, I see. Okay.
Oh, wait, but once how'd I do that? Once I did that, it changed like the configuration and folded this panel up somehow, I'm guessing. I do not remember how this was getted. But somehow it did not like these being down with that being bent. So we get to see the other configuration though. Okay, so yeah, so the green panel stays up most of the time when we're just joining gears. The purple panel folds down over the bumper so that there's no gap for the gear to like fall in. Because that was some teams' problems. If you didn't have something that actually moved out over your bumper, when you ram into the wall, the gear could like land, kind of go into whatever that gap was and fall onto your bumper and not into your robot where you wanted it. So once the gear was here, these pneumatics would actually push out. So you can see where the pivot is mounted. I'm trying to think how to show where the pivot's mounted. So I don't actually even remember where the pivot's mounted. How does this work? There's something missing. This looks confusing right now. There was another bar somewhere. So somehow this is mounted, this hinge is mounted in a way that when you push this out, this forward Lexan, like the cover right here, right, would swing back this way around this pivot, and this part in the back would push forward, so you'd push the gear out. So you'd have like the C holding and the whole thing would push like that, right? Okay. So you'd get this, where my thumbs are would be pushing the gear forward and actually push it onto the peg. So that was a design that was built by several other teams first. So we did a lot of research into how some of the best gear runners in the world were working, how they like designed everything. And there was this weird kind of, you had this middle pivot kind of along this C that allowed you to open up the front and use the back to push out. And they're actually like these, their little blocks back here made that transition a little bit easier. These are like routed out of HDP, I think. And those would help force the gear out. And then somehow this panel is upside down. I don't know what's happening here. This clearly didn't stick in the ground, right? If you can imagine this whole thing flipped up 180 degrees, I don't know why the mate is wrong. But basically, instead of this being down here, this is up behind the gear.
Right.
So what that was for was that was just a trigger plate. So when the actual little spring that you had to put the gear on went through and hit that panel, it would flex backwards, and the bottom of this would run into this bump switch. So we would know that the spring is all the way through the gear, and it would basically auto score it. So I think this was on driver. The driver would have a button that would basically put it into auto score mode. So we knew we were about to try to score, and it would basically wait for that bump switch to be hit. And as soon as it was, it would fire the pneumatics and score the gear as soon as we had gotten the peg in one of these holes for it. These outer parts were all designed so that they sloped back, right? You can kind of see how they're pointed towards the gear. So that if we were off and we ran the spring into one of these, ideally it would slide this way and force it into one of the gaps. So we were trying to just make our target wider, since the spring that the gears were going on was really flexible. We tried to widen the target for our driver instead of just being the inner part of this gear. He had a little bit of room on the outside that if he hit, you could kind of force it in and still be able to score the gear. What else? There was like a panel on the bottom so the gear didn't like fall down and get caught, because for a little while we didn't have that, and as we released, the gear would drop enough to where the bottom of the gear would hit this tube, and that would mess things up. So we eventually fixed that, and this whole assembly was mounted to the robot just with the quick release snaps that we used for bumpers. So there were 4 of those, one in each corner, so the whole assembly could be taken off as one part. You just have to unplug some air tubes. So it was entirely built that way. And then the final thing it could do was when the purple was down and you brought the green down, it would let you roll balls into the shooter assembly. Right, so you would cover up the gear slot, and you'd have a path for balls to roll in, so that we could ideally do the autonomous, where we need to drive into the hopper. This would be folded down, because this would be one of the things that hit the hopper panel, like the release trigger, and then balls would all funnel in, and ideally be shooting out of the shooter as they're funneling in to go up into the goal. Okay. Any questions about the gear backpack or the climber or the gear mechanism before we get into the shooter?
No.
Good. Okay. So the shooter, like I said, was largely based on the Killer Bee shooter from that season. That might have been a bad idea. That worked. Okay. So all we wanted to be able to do, all we knew we wanted to be able to do was be able to shoot Auton and kind of tune in a single shot location that would let us take enough balls from the hopper on the side of the field and put as many of them into the goal as we possibly could. So some of these things I'm going to describe are definitely innovations that the Killer Bees design that we used, and a little bit of stuff that we modified and did our own way. So things that were definitely ours are like I don't think theirs was all shoulder bolted. Their entire thing was 2x1 construction with actual bearings and everything for the hex shafts, as far as I remember. And none of theirs was sheet metal, right? So we did it all with sheet metal. This also mounted with 4 quick snap latches. So we had there were pegs that would locate the whole assembly, and then you would use the quick snap latches to actually hold it on. Since this whole assembly didn't take any vertical force, right? Nothing was ever trying to pick this up out of the robot. You didn't need much to hold it in. You just needed it to be located. So the pins would locate it. And then, so like the way the pins would work was they would basically just be, they were just thunder hex that would go through these holes. And then there was just a bolt coming out the top that would locate it through one of these holes. So that would stop it from sliding in any direction, and then the latches would just hold it from coming up or down.
Okay.
So that actually was really nice in that we could swap an assembly very easily. And the reason we designed it was so that we could pick it up and have it shoot either out the left or the right of the robot. The belt bed for us was the same belt system that we had been using already. So we had been using 3D printed pulleys. This is also why we own a giant box of 3D printed 18-tooth half-inch hex pulleys is from this season, because the first version of the robot used dozens of them, and this version still needed quite a few. Right? There's like 10 here. So each one of these had a belt, and it would just funnel balls back to the shooter. It was powered by a Versaplanetary here with little standoffs on it, and so the belt just ran like that. So in modern, we would probably have some sort of 3D printed thing to try to do that, although you couldn't run it around the standoff if you did that. That was kind of annoying because you'd have to put the belt on and then mount the thing and then get the belt on for this side. So it was not ideal, but it worked okay. And then this was fun, where one of the reasons why it was mounted at this angle was so we could use the mounting holes from the Versaplanetary to mount this Lexan dividing thing. So we didn't have to build like some other assembly. We just mounted the Lexan to ramp the balls in so they didn't like get caught in any like weird spot. We just used the motor or the gearbox assembly to be the mounting for that, and it worked fine. We probably very easily could have like mounted something up on this side rail, right, and that had mounting holes for this and had it on both sides. That would have worked too. Okay, so yeah, balls would come in. We would run the belt going towards the actual shooter tower. And the shooter tower is where things get a little bit more interesting. So the shooter itself was a single 775 Pro powered from this 12-tooth 3mm pitch pulley. So it's on the end of the 775 motor, right? And there was a belt up to what I believe, what is that? That's a 60 tooth, so it was 12 to 60, so it was 1 to 5, or 5 to 1, however you want to call it. Gear reduction from here to here. And these were 4 of the Fairlane wheels, the white Fairlane wheels that we used for multiple other things. We had them in 2015, 16, and 17. They were one on all of our robots. And then there was some version of them on 18 too. 19 was the first year. We had Fairlane rollers, like the white nitro rollers, on 4 straight years of robots until 2019. And then on this other side, we had a 775 Pro that would power this top roller. Okay. And from there, you'd have another 12-tooth pulley, and it would power, what is this? This is like 30-something, 32. So it would go 12 to 32 here. And then on the other side, if you're not paying attention, they kind of look the same, but they're not. So you would get a 30 right here, and then a 32 again, right? So you get a small gear reduction going from the top roller to the next roller. So now this middle roller is spinning slower than the top roller, right? And then we do the same thing again, going from 30 to 32 on this next roller. So the bottom roller is spinning slower than the middle roller, which is spinning slower than the top roller. So as soon as the ball touches, right, it's going to accelerate as it goes up to its final shooting speed up here. Does that make sense?
Yeah, I think so.
Yeah.
So you want to have more torque down here to accelerate the balls that are basically not traveling fast at all, right? They're traveling 0 speed up. Right, they're getting moved in through this belt, but they have a 0 velocity going vertically. So the bottom roller helps accelerate them first, and and they hit again, and they're going a little bit faster,
Oh,
and
God.
finally
Okay.
to the exit speed of the top roller, of the actual shooter roller.
That makes sense.
And so that also helps with, and it helps on jamming too, because as you go to your next roller, you're going to try to gain distance away from the ball below it. Does that make sense?
Mm-hmm.
Right? If they were all geared the exact same, as the belt slowed down, they would all like kind of stay together. If they were touching when they went in, they would stay touching the whole way through. But with this, they try to like space out and try to accelerate away from the ball that's in the stage below it. The width of this is very important. So this whole shooter assembly, it comes out roughly that it's about a ball and a half wide. Right? It's not quite.
Mm-hmm.
The when you actually feed it through, it ends up not being quite 2 balls wide. And why that's helpful is you don't get a lot of jams because you end up feeding balls kind of in like a zigzag pattern.
Okay. Oh, right, yeah.
Right, you'll get kind of one here and one that's kind of spaced kind of above it and to the right, and then you get one above it and to the left, and you'll keep doing that. And so the stream that comes out is kind of this like zigzag stream of balls that never really wants to jam, because you always have the next one, like if you get 2, one of them kind of gets in and funnels up, and the second one gets pulled in after it. And you don't really, and it pretty much never jams. You didn't have to have any sort of like slots for them or anything. So a lot of the 2 ball wide shooters that exist probably get a slightly better throughput because you're able to put actually like 2 balls in the air at the same time. These ones largely you get this like zigzag kind of shooting pattern. That means they don't really ever hit each other, even if they're coming out at weird angles, because they're almost always one of them slightly in front of the other as it's firing most of the time. Let's see what else. So the back here is a little awkward, and it's kind of interesting to figure out. So basically it's built to have infinite adjustment. So as you make these rods, you can change these rod lengths to be whatever you want to change your compression from this back hood to the shooter, right? So we could like, you could fine tune this really small details by just like adding a washer here, right?
Mm-hmm.
It bolts in from the back to this tube. So if you just like add a washer or a shim, you can get down to really, really fine compression details to figure out exactly what length you want on all of this just by adding little tiny bits of material and things to change that compression number. And then the same thing with the angle of shooting is the way this mounts. This is just mounted around this bearing. And so this outer plate here clamps it in place. So if you loosen these 3 bolts, we actually ended up putting a piece of rubber in here and doing a couple other things to keep it locked in the location once we figured it out. But basically, if you loosen these 3 bolts, you could then tighten it. You could adjust this angle however you wanted. You could rotate this plate. You could tighten those back down and set an angle, even if you didn't know what angle it was going to actually shoot out when you were designing it. If we had redone that, we would have probably put a few more bolt holes around here, because one of the things we eventually did was we also put a bolt through one of these and a washer to clamp up higher. So it's further out on the lever from where the pivot is. And that helped stop it from adjusting when we were actually shooting it, because it would like wiggle a little bit when we were shooting. But having the bolt out further helped a lot with that. And so all of this is pretty basic sheet metal, right? You just have a little piece with a straight 90-degree flange here. And that's all that allows it to bolt here. The same flange back here allows you to bolt the back on. The gap that existed here was covered by a piece of Lexan. So you would just have, there was just a piece of Lexan that mounted to these 4 holes up here, kind of between the standoffs and the plate. And then it was cut in a way that let it just basically get backed and pushed onto this plate.
Okay.
But you could still adjust the height because it wasn't mounted anywhere in this plate.
Right.
And then we also had a piece of rubber mounted on top of that. That gave it more friction on the back, because the way these balls worked, it worked better if you had a lot of friction on the back, so you could roll it the whole time instead of ever having it slide. Let's see. Not in CAD. There were standoffs clearly between here and here, so that this, this wasn't floating in space. So and largely this worked pretty well. Like with the shoulder bolts into hex shafts worked okay. This is definitely a place where you'd probably do shoulder bolts and hex shafts here instead of our like the standoff tubes or anything like we do for our intakes, because it allows you to get a smaller pulley. If you try to do our spacer tube and a roller on top of that, even though the roller is about the same size that you can end up doing, the pulley can't be, right? Because normally we have to clamp on a pulley on the outside. So if you want to get a smaller pulley in here to kind of keep the diameter kind of the same the whole length, you have to have a hex shaft running through it that it's actually rotating. And you're not really worried about your structural strength here since it's not ever running into anything, right? This doesn't leave the frame perimeter of the robot. This is never getting hit by anything. And if you are worried, you could easily put a standoff like crossing between here and here, like this hole, right?
Yeah.
If you wanted to put a standoff, you could. There's nothing stopping you from doing that if you're worried about this whole thing flexing or something. Let's see. So yeah, this plate was designed to mount a camera or a flashlight or whatever else you wanted for aiming. And you could aim it however you wanted because you could adjust this angle too. I think that's most of the shooter. There was one of the weird things was though that it was we did design it to be able to pick it up and pull it out of the robot and turn it around, right? So because of that, we had to have really long wires running to it because we literally had to be able to pick it up a good 2 feet or so, to rotate it and set it back down. So it was always just set on this big like nest of cable that was just like wrapped under it and then pushed down, made sure to force down and just like just snap latched into place. We probably could have like unplugged it every time, but we just didn't want to because you had to unplug the encoders and everything too.
Yeah.
So we just made really long cables and just dealt with it. It's probably not the best option, but it was the one that was going to keep us the most reliable that season. Okay. I don't think there's any more. I don't know if there's any more better video from this robot or anything. Yeah, because our recap video from that season is like the full, that's the banquet video. So there's a lot of like everything. There's some more video, but we'll watch a lot of the same video from the other version. Where are? This is the year of Will. This is the year of Will arguing.
The famous argument.
The famous argument where he had one of the longest pick times ever. This is a photo of us watching Las Vegas after Alamo wrapped up, and we were supposed to be like cleaning and leaving our pit. We were like, no, we're not going anywhere. And I like got a stream on a laptop somehow through like a Wi-Fi hotspot or something, and we just like had a bunch of people all watching the end of Las Vegas because 118 and 148 were there.
Okay.
So we
They
were
lost,
just waiting. We were like, we're not going anywhere. We're just watching this match now.
They lost, right? 148 and 118, didn't they?
Did they lost? This is Citrus in 987, or did
I'm
they?
pretty-
Oh wait, did they play together? Yeah, they did. Yeah, 118.
They played together because it was like
and they lost to
Texas
Citrus in
versus
97, I think.
other people.
That sounds right. Yeah, I don't think there's much others of our actual robot doing anything in this video.
We can watch 118's reveal video.
What else happened that season? That we ended 118's regional win streak at Hub City, even though we didn't win the event. We beat them in the semis because they fell and had many broken things. But then we managed to not win finals, which was sad. because we needed like one extra gear or something in the final match of match 3. What is this? Well, this is a problem, and we need to figure out how to not have that exist. I have no idea what that is. I don't know what channel that is. I have no idea, but that's an investigation for for another time. I'm very worried about that. Yeah, I don't think we have a ton more other 2017. Oh, there's some pit time lapse stuff from IRI, but not. Just trying to figure out if we have IRI where we actually shoot, because IRI was the only time we actually shot. TRI, our shooter, was not quite functional yet. We basically, like, to get it functional, we set up, because we didn't have a practice field in 17 very much at all. So we ended up setting up the goal in the foyer where like our 2020 goal is, and getting enough like carpet and stuff set out, and then we just ran stuff for a long time and tuned it all to where we could get the shot, and then got it to where it would actually work in auto. Somewhere there's definitely a 2017 auto video that exists. I'm pretty sure it's on our YouTube.
I thought we released it before, like
We
IRI.
did. We definitely released it before IRI. I don't know if we're gonna be able to find it though, because we have a lot of video from a lot of events. 2018. We have a lot of 2018 video on our YouTube page. Okay, Remix 2017. We have an airship timeline. That's cool. NTX 2017. Robot Roundup 2017. There we go. So this was us practicing the Hopperado. So we eventually got the shooter. We did get the shooter working pretty well prior to IRI, and going into IRI, it was okay. I think we shoot this match.
2, 1, go!
Nope, we do not shoot that match.
Programmed awesomeness, autonomous mode, 4206 misses on the red airship here.
Oh no, we do. You just, oh no, I forgot about this. All the IRI video, you can't see the shooting.
Oh yeah.
The camera's from this side, so we're over here shooting. You just can't see it, and it's very frustrating.
Techfire 225, let that fuel fly. Loretta Line.
So we actually we put in a decent number.
Flying fast and furious.
Yeah, so we put in like 30 balls.
Pretty even on the field count, but red.
Nope, that's not us. We put in 24 balls. There we go. We're red. This was a very confusing IRI, right? Because your blue scores on this side, but blue's playing over on that side, and the hoppers were just like non-existent because you could never see who was scoring. It's not a great stream. Okay. Any other questions about 2017 before I stop the recording?
I don't think so.